Clark to talk.
Thank you very much. So what's happened? So we first started off by talking about how you kind of extract a notion of sort of open subset and closed subset from a topos. And we talked about this sort of recoulement idea. I'm not going to be able to talk a whole lot about the stable story, which is interesting and a source of great richness. But I want to just mention something in response to Piotr's observation. And so let's think briefly in the stable situation about this recoulement business. So suppose again, let's return to this sort of circumstance where you have an open subset and you have its closed complement. And the rules say, I call this J and I call this I. This is clear. And I'm going to do things like look at the category of sheaves of spectra, say, or sheaves of complexes of abelian groups on these categories. And I'm going to see a recoulement there, right? So if I look at sheaves on U valued, say, spectra, I might as well do that. I look at sheaves on X valued in spectra, and I look at sheaves on Z valued in spectra. Well, I get this same sort of recoulement, and I actually get extra functors. I actually get an I upper shriek that I will write down in just a moment. So I get this J upper star. It has two adjoints, J lower shriek, J lower star. And then over here, well, I have this I lower star, and it has two adjoints, the I upper star, and then this thing that I get because of the stability, or actually just the fact that I have a zero object and enough, just actually that, I get this extra adjoint here. And I sort of wrote down the sort of table of I wrote down that 3x3 square where you have the sort of exact rows and columns. The rows and columns are fiber sequences. Now, what Piotr observed is that if I now decided that these were schemes, and I had a closed subscheme and its open complement, then, well, what should I be looking at? Well, first of all, I can't talk about, I can talk about quasi-coherent sheaves on Z, but that doesn't form a full subcategory of quasi-coherent sheaves on X. Bachstein. Right. So if I look at modules over FP, that doesn't form a full subcategory of modules over Z. The Dirac category of modules. It's not a full subcategory because of the Bachstein. So that means that when I think about quasi-coherent sheaves and I want to break it up using this this open-closed decomposition, the way I have to do it is different. Instead, I have to look at quasi-coherent sheaves on X that are set theoretically supported on Z. That is to say, I'm going to be looking at...
That's the open part now?
That's the open part now. Exactly. This is exactly the issue. If you look at how the recoulement goes, it goes like this. The recoulement knows which side is the open side and which side is the closed side, right? The recoulement knows. And what you see here is that, in fact, on quasi-coherent sheaves, it's flipped around. The closed side is actually sitting on the open side, and the open side is sitting on the closed side. This has a real impact when you start thinking about things like the spectrum of a symmetric monoidal stable infinity category. So there's this thing called the Balmer spectrum. And if you look in Balmer's paper, so this is defined as a spectral topological space whose points are primed thick tensor ideals. And he gives that thing a topology. And if you look at the way he gives that thing a topology, and you compare it with how you learned to give the topology on spec of a ring, you'll see that he has exactly the opposite conventions. when he's writing down, like he writes down, you know, the analogs of these DFs that you see in algebraic geometry. These are those sort of, those are basic opens. I'm not using basic as an insult. I mean that it's a base for the topology, right? It's the locus of non-vanishing of the function f. And the analogs of these things are actually closed in Balmer's spectrum instead of being open. And there's a reason for that. Why does he want that? Well, he wants that because he wants it to be the case that if you take spec of the category of quasi-coherent sheaves on X, technically speaking, he would pass to a subcategory of this thing of finite objects, but let me skip that part. Then what he wants to do is he wants to recover X, for X, a quasi-compact, quasi-separated scheme. And that's a true thing to say if you use his definition of the Balmer spectrum. But with his conventions, this duality happens, and it's precisely because of this. However, if you're more motivated by this kind of thinking, this sort of more topological way of dividing things, then this is actually an unnatural thing. And what you'd prefer to do is you'd prefer to have a version of spec that actually gave you the opposite of X instead of X itself. And that's sort of reflective of the fact that when you think about this open-closed decomposition, I mean, when you think about an open subscheme through the lens, here's Z and here's its open complement. When you think about this through the lens of quasi-coherent sheaves, what's actually happening is that you're thickening this thing up to an open, and that's the thing that you're putting here on this side. And the complement, quasi-coherent sheaves on the complement of Z, actually are quasi-coherent sheaves away from Z. So this thing actually functions more like a closed than an open. Okay, so that's why you felt that tension between the version of the story that I was telling and the version of the story that, this is a long way of answering that question, but it's an important point. And actually, if you look now this is part of something that I'm just not going to be able to talk about, but there's a different way of defining the spectrum that doesn't just give you a spectral topological space anymore, but gives you a more general locale. And that more general locale is actually organized around this way of using geometry to divide up your category. I feel like I'm being too vague. Am I being excessively vague? Need to say something?
I have a question.
Please.
So Walmart spectra is something you can put QCO into, but
Mhm.
not a priori sheaves.
Well, you can put sheaves into there. You absolutely can. And you absolutely can. And what you'll get, let's see, if
Just the last comment you made, I didn't quite understand like how what change you're making to get a locale.
oh, that's because I didn't tell you. But I'll tell you in words. So what you do is you take this, not heck with it. I'll just tell you what it really is. It's just a cool story, and I'm just going to tell you. So I learned this point of view from a paper of Koaoki, which I think is called the Sheaves spectrum adjunction. I'm mentioning that because he's an example of a young homotopy. So in the Sheaves spectrum adjunction paper, what I realized that you're doing is, well, so like, remember when we were thinking about topoi? Like, when we were thinking about topoi, the way we got the opens of a topos was to look at the -1 truncated objects. Story. And remember that a -1 truncated object, well, what kind of thing is that? Well, I mean, everything's got a map to the terminal object, but I'm going to require that this one be a monster, right? So that means that if I form this pullback here, then, well, what am I looking at? I'm looking at isomorphism or equivalences here. That's what it means for the map from F to the point to be monomorphism, which is the same thing as being -1 truncated. So this is what we were talking about on the very first day. And now, so let's think about how you might generalize that to categories that aren't just the category of that aren't just topoi. Well, what kinds of categories do I want? Well, I'm going to actually I'm going to take categories, but I'm also going to take categories with a symmetric monoidal structure on them. In the topos case, the product will serve as that symmetric monoidal structure. But more generally, I might just be able to work with any symmetric monoidal presentable category. So if I had a presentable, so if C is a presentable symmetric monoidal category, by which I mean that the symmetric monoidal structure preserves colimits separately in each variable, then you could try to mimic this definition in the following way. You could say that the opens of C should be the idempotent coalgebras. What are idempotent coalgebras? Well, they're really just maps from C to the unit for the tensor product, such that when you tensor with C again, you get an equivalence. Oops. So if I take it's a map like this, such that if I tensor it with C again, then I get an equivalence. This is automatically a E infinity coalgebra. I don't have to add any more structure to this picture in order to give you the full E infinity coalgebra structure. As soon as you have this condition, it just shows up. This forms a locale. This is a locale. It's not usually spatial, but it is a locale. So it's a locale, but that might not come from a
Locale, that's a concept with finite intersection and arbitrary direct sums.
yeah, that's right. And the distributive law holds.
And what would the let's say unions look like for idempotent coalgebras?
Well, so if I have, I mean, the unions are exactly colimits here. Like this is a
Oh, this category itself is a poset.
this
then.
category itself is a poset. That's right. This category itself is automatically a poset, and so the colimits are unions and the limits are intersections. It's really that simple.
C is an object of C.
C is a presentable symmetric monoidal category.
It's on the right.
Oh, this is a yes. C is a this is a idempotent coalgebra. Sorry, thank you.
So to specify the structure, the E infinity structure, it's enough to just have like an augmented object, which is idempotent in that sense, and I automatically get the coalgebra structure.
That's exactly right. Thank you. Yes. Yeah, that's exactly right. So you don't have to provide more structure than just this, and you get this whole picture.
If you would take idempotent algebras instead, would you still get a locale or
Well,
the same actually?
if C is stable, they're the same.
Okay.
Yeah, so that's exactly the next point that I'm going to make, which is that
I'm gonna not say anything.
sorry, and I'm not criticizing you. I'm very grateful for the help because it's keeping me on track. Otherwise, I'll just get distracted. So if C is now stable, then actually idempotent algebras and idempotent coalgebras are the same thing. He's leaving. Oh no. So if C is stable, then it turns out that idempotent coalgebras and idempotent algebras are the same thing. If you have a, why did I do that? If you have a idempotent coalgebra, then you can get an idempotent algebra by, pushing out A. And now this will be an idempotent algebra. And so idempotent coalgebras and idempotent algebras are the same thing. And so then you can define the opens of a stable infinity category as the locale of idempotent algebras. And this is another kind of spec. It's a much larger spec than Balmer's spectrum in general. You can define using this, so you can define spec C as the locale of idempotent algebras in C. And this is a locale. This is a different spec from this spec down here. So maybe I'll all here so that we remember that these are different. In general, this is much larger. It's a locale that's not even usually spatial. It's spatial if, say, your C is compactly generated and the compacts are the same things as the dualizable objects. That kind of condition will give you that.
Always small.
This C is presentable.
And the spec C is always small.
Oh, yeah. The spec C is actually always small. That's not obvious, but it's true. Turns out this is always just a set. And well, so what happens? Let me give you an example. So let's say that you take spec of quasi-coherent sheaves on your favorite scheme. And the question is, what answer do you get? And well, you're not going to get X, you're going to get X op. What do I mean by X op? Well, what I mean is that, remember, X is a spectral topological space. I'm talking about just the Zariski topological space here. That means that it's a profinite poset. I know how to take the opposite of a poset, so that's what it is. So you actually get the opposite here.
This duality has a name. Is this the Hochster duality?
The Hochster duality, that's exactly right. Yeah. Yeah, this is the Hochster dual of this spectral topological space. Yeah, so this thing is sort of turned around completely. I would like, for those of you who think about things like chromatic homotopy theory, I would propose that you might think about this form of the spec. By the way, the fact that this form of the spec doesn't coincide with Balmer, or with the opposite of Balmer's spectrum, is the content of the telescope conjecture, or the failure of the telescope conjecture. Yeah.
So in this case, there is no compactness implicitly floating around.
Not at all. That's right. These are presentable categories, but otherwise,
You could ask for the algebras, the idempotent algebras, to be compact as algebras, right? So that would be like a finite presentability.
Yeah, right. Yes.
Is that thing in general then closer to the Balmer spectrum?
I don't think I know the answer to that question.
I think it's quite close.
I think it's quite close.
Idempotent algebras are supposed to be also sort of resemble the compact opens of the Balmer spectrum.
That's right.
And I think if you kind of look at this through this is something Robert told me at some point, so maybe
Okay.
similar.
Robert says a lot of right things. So. Yeah, I think that's an interesting question. I haven't thought that far. I probably should have. Okay, so yeah.
So you said this thing is not in general spatial.
Yeah, that's right.
Do we get the Balmer spectrum by taking its points?
Yeah, I think something like that is true. But I don't want to quote it because I can't remember what generality that's true. And I might have some pretty heavy conditions on the stable infinity category. So I think that's right. So I think that if you're in the circumstance where okay, let me see if I can say this correctly. So I think if C is compactly generated and dualizables are compact, so you rigidly compactly generated is the phrase that I'm looking for, then I think that that the points of this spec are the points of the Balmer spectrum.
It is not.
But it doesn't have enough points, but it's not, it doesn't have enough points. So It's not spatial, as you say. So you can talk about the points of a locale, right? And that'll give you a topological. That topological space, I think, will be the Balmer spectrum in the case that I said. I'm kind of hedging a little bit because I don't remember how much of what I said is actually necessary for that claim, but I don't want to state something completely false, so I'm going to try and hedge. All right, I have to be careful about. Oh, I have to be careful about time. I started at 9:30, didn't I? Okay, I'm not done yet. Okay, all right.
No.
But I got freaked out because I saw 52 and I'm like, oh, that means I'm done. But can't possibly be right. I hope it's not right because I have something more to tell you, which is that what we've done in this exogamy story is we've said the following. We've said that if you've got a topos that's stratified, then what we can do is we can extract from this thing a certain stratified space. But it's not just a stratified space. And so I want to talk a little bit about what kind of thing it is. And this goes back to this issue about the fact that, well, in the case of the tall topos of a scheme, I made the following claim. I claimed that this thing can be recovered as the category of continuous functors from a certain profinite stratified space, which we're regarding using this layered infinity categories business. We're regarding this now as a profinite layered category. And so that profiniteness means that it's got a topology. And I'm going to talk about continuity of this topology. And then here I'll just write the category of spaces.
Did you end up last time giving us a full definition of what you mean by continuous?
Nope. I haven't told you what continuous means. I haven't told you what gal means. And actually, secretly, I also haven't told you what an means, because it's not just the category of anima. It has to be whatever continuous means. It has to be that kind of topological category of anima. So what is that? So this is what the condensed formalism allows you to do. I'm going to say everything I'm going to say about the condensed formalism in this box. But are you going to say more about condensed stuff?
Not that much. I mean, yes and no. I think in terms of background, probably.
Okay, so I'll say the following thing. So if you've never thought about this stuff before, let me just tell you what the point is, and then I will ask you to accept that this allows you to talk about things like continuous in these sorts of situations. So what's the story with condensed stuff? The story with condensed stuff is that infinite structures usually come with topologies. Right, so if you're talking about sort of infinite dimensional vector spaces and you don't have a topology on that infinite dimensional vector space, you might feel some discomfort. In fact, you probably won't be able to prove much, right? So with the presence of topologies, of topological, those things allow you to get handles on those objects. So in the condensed world, what's the story? The story is that we're going to think about inverse limits of finite things as providing you with topologies. So on the other hand, the interaction between the category of topological spaces and the interaction and the algebraic categories, like the category of abelian groups and so forth, is really awkward. Right, so you have issues where you have like there's a failure of abelianness, so it's hard to start doing things like if you look at the category of topological abelian groups, any reasonable category of that, it's not going to be abelian. You're not going to be able to do homological algebra. You can do quasi-abelian things if you're careful, but it's always sort of fraught. So to try and deal with that, what you do
Then AUGHT or
Yeah.
fraud as in RAUD?
Broad.
no fraught with a T on the end. I'm not accusing anyone.
Recording.
Entirely the wrong setting.
It's being recorded.
Every word. Every word. So, Okay, so what's the idea here? Well, the idea is that I want a better marriage between topological structures and algebraic structures. And so the idea is, well, first I'm going to take the category of topological spaces and I'm going to peel off a little piece of that that really functions as an algebraic thing. There's actually two sort of natural things that you can think of. The first thing you can think of is I could look at profinite sets, aka stone topological spaces. So these form a full subcategory of topological spaces. And you can work starting with these. Another option is that you can remember that the category of compact Hausdorff spaces is itself it's an algebraic category already, because it's the category of algebras for a monad, namely the ultrafilter monad. So it already is algebraic in its structure. And so you say, all right, well, I'm going to generate the category of condensed anima under colimits from one of these two categories. And it actually doesn't matter which one you take, because the answer will be the same as soon as we identify what relations we want. And so what you end up doing is you end up looking at the topology on these categories. The cover is a quotient map. You have a growth in the topology on these things, and that permits you to talk about sheaves and hypersheaves and all sorts of stuff. So the category of condensed whatevers, so C can be any kind of infinity kind of wire, is the category of hypersheaves on the site of compact Hausdorff spaces valued in C. That might sound like a nightmare to these descent conditions. But the good news is that there's an even smaller site that generates these two. And there the coverings are actually split, which allows you to turn this hypersheaf condition into just a condition about preserving products. Now, the spaces that do that are kind of weird. They're these extremely disconnected spaces, which are, I don't know, you don't spend a lot of time with them, so they're kind of unusual. But anyway, so that's just telling you that this thing has really nice formal properties at the end of the day. Okay, that's literally all I want to tell you about the background of condensed. It's like, and that's actually part of the point, is that you know, for our purposes, it was the definition was enough to really do something useful. So like, we're not really getting very deeply into the world of condensed math for the statements that I'm going to make here. But the point now is that, well, gal x, that's something profinite. So that means I'm taking an inverse limit of finite things. I haven't told you what it is yet, but I'm gonna. But it's something profinite. And so that means I can take those finite things, regard them as discrete condensed categories, and then take the inverse limit there in the condensed world. And that gives this thing a natural structure of a condensed category. This CTS is going to be in reference to the fact that I'm going to take maps of condensed categories, not just raw categories. The only other thing I have to be cautious about here is the fact that the category of anima is a condensed category, but it's, and you might think, oh, I'm just going to take the discrete category, condensed category. And you're right, except that you have to take discrete in the presentable sense, not discrete in the category sense. It turns out you get two different answers that way. If you didn't understand what I just said, don't worry, it's not a big deal for the purposes of this talk, but just understand that there is a subtlety there. Okay, so what is this gal x? And I'll actually just define it for any. So this is going to be for any coherent topos. So the category gal x, this is going to be a condensed category. So that means that for every profinite set, I have to give you a category, and then I have to convince you that it satisfies this descent condition. So for every profinite set k, I have to try and tell you a category, which is the k points of this condensed category. And what am I going to tell you? Well, I'm going to tell you that I want to look at the morphisms of topoi. So these are the, you know, the lower star functors in that morphisms of topoi. From where? Well, from the category of sheaves on this topological space into your topos X. And now, well, I actually can't just take all of these, or I can, but I'm not going to. I require that this coherence is a certain sort of compactness condition. So this is analogous to the sort of situation that we saw with spectral topological spaces, where the maps that we had to take were the quasi-compact maps, the maps such that the pre-image of quasi-compact opens were open. So I'm using a similar condition here, which involves this notion of coherence, which is sort of the higher categorical version of compactness. It's sort of compactness and then compactness conditions on diagonals and higher diagonals. It's that kind of thing. So this is now a condensed category.
You're missing an op.
I'm missing an op.
Yeah, because points.
Oh, thank you. Yes.
This is just some stupid thing. Yeah.
This is a stupid thing, but it's a stupid, confusing thing as we go.
Extremely confusing.
There was I've told this story in public several times. There's a paper that Peter and I were reading, and they had two. I'm gonna name names. They had two of these geometric morphisms of topoi, right? And this is what was in the paper. And they had this eta. Question. You see this in a paper. What is the source of the natural transformation eta?
Obviously G, because it's not what you.
Yes, you understand the structure of my, yeah, that's right. This was their notation for a natural transformation from G upper star F upper.
Oh.
Yeah.
Oh.
And I remember
From F upper, sorry, that's the same thing.
Yeah.
Sorry, I wrote it the wrong way around. F upper star to G upper star. Or equivalently, G lower star to F lower star.
But I remember exactly where I was when discussing this because we were talking online and like I don't understand, like all of their theorems just seem like they seem to have this problem. And then I was scrolling through the document for like a really long time. I found, okay, on page 87, they say that they make this terrible convention.
Giving us too much information.
I think it will still
It's
not be
still-
easy to.
I don't think it'll work.
Yeah, yeah.
87 of every single paper.
Every single paper.
There was a, but I shared, I mean, I was tearing my hair out. I remember being in my office thinking like, I spent 4 hours trying to figure out how to, really awful. Okay, so what am I telling you here? I'm telling you that for the atoll topos and lots of topoi that are like it, you can actually reconstruct them as just functor categories, provided you're willing to say continuous functors, provided you're willing to move into this condensed context. So I'm telling you that topoi like this are recoverable from these things, these gal x's. Now, what kind of thing is gal x? That's the next question that you can ask. Well, what is this thing, this gal x? Well, I wrote it down. It's a condensed category, but it's actually better than that. Let me specialize this story now to the case of the atoll topos of a scheme. I can really say precisely what this category is. In fact, interestingly, it's a one category, and it's the category of points of the atoll topos, which you can think of as maps from spec of an algebraically closed field into your topos. And the morphisms are specializations. Okay, so what does that look like? Well, as we talked about during Lucas's talk and in the last time, I can think about the atoll topos stratified over the Zariski topos. And so I can try and think about what this object looks like. And it looks like a stratified space, a profinite stratified space over the Zariski topological space. So that means I can just tell you what the strata and the links are, and then say some kind of wishy-washy things about continuity, and you'll see that what this object really looks like. Well, and what is it? Let's think about it just in the case of spec Z. I'm going to look at the atoll topos of spec Z, and I'm going to look at this Galois category of it. And what did we see? Well, we have these closed points. These are closed strata. But what do they look like? Well, they're each BZ hats, right? These are the absolute Galois groups. These are the absolute Galois groups of the finite fields. And then we have the absolute Galois group of Q, which is a mystery. And then I have to tell you what the links are. And the links are going to be given to you by maps. You can think about these things as maps that go from the absolute Galois group of QP, the classifying space of the absolute Galois group of QP, mapping in these two different ways. In this direction is specialization, and in this direction is inclusion. It comes from the inclusion of the absolute Galois group of QP into the absolute Galois group of Q. And you have one of these, you have this sort of spider shape. That looks like. Do these eyes. You can think about each of these things as a circle. These circles are wrapped around each other in interesting ways. And then this is telling you about how that thing embeds in the bulk. It's telling you the deleted tubular neighborhood of that circle. This is the map from that deleted tubular neighborhood down to the stratum. And this is the inclusion of that deleted tubular neighborhood into the complement of all of those knots that we were talking about.
How do you specialize if it's a deleted tubular neighborhood? Sitting in there.
Well, no, I mean, I have a deleted tubular neighborhood and I'm just gonna collapse it. Yeah, so if I've got, if I imagine this thing as a knotted torus and I've got the sort of filament of wire that gives me the circle itself, then I'm really just collapsing the.
Is this a recollement, like each of these spider legs?
No, this is not a recollement. This is a décollage. It's a different French word. It's the it's this picture of the strata of my stratified space. These are the strata here, and then the links, these dots here refer to links. But it's represented as a diagram. It's indexed on the subdivision of the poset, or profinite poset. So this is what we saw in Lucas's talk. So this is a picture of Galois spec Z. And it's this sort of very rich, very interesting picture of Galois spec Z. Let me tell you some more facts about these Galois categories.
So I should think of like not just the points for each BZ hat, but there's a BZ hat in this category. And there's a natural transformation basically as a layered category from the BGQP thing to the BZ hat and also to BGQ. Is this like the picture of the category?
Yeah, this is a picture of the subdivision. Yeah, this is, I mean, yeah.
Actually, you would have to put like a BZ hat there instead of.
More like a Siegel space picture.
Yeah, this is a Siegel space picture. So the category I'm drawing is like this spider category that I'm drawing here. This is the subdivision of spec Z with the Zariski topology. So this is a profinite poset. I'm taking the subdivision of it, and it looks like this spider.
Yeah,
and
the
so
strata are like the.
Yeah, this is the stratum, this is a stratum, and this is the link between the two strata. So this is like the deleted tubular neighborhood of this in here, or in the bulk. So I thicken this thing up, right, and I intersect it with the open complement, and I get this thing. Is that a better way of saying it? Probably. I should have said that's it.
Yeah, no. So in the category, there's really just the maps from the BGQ straight into the BZ category.
So, well, I love this shirt. Can we talk about that? Yeah, no, that's right. That's right. Yes.
You say it's just the one category, and I guess I have two questions about that.
Yeah.
Does that mean what I think it means? First off, like, is it?
Yes.
Okay.
That was easy.
But what do I think it means?
Is that your second question?
That was not the second question. No. So it's really just one category.
Yeah.
This is the weird thing I've observed in many of these cases where like somehow the one like the stratified homotopy types that show up actually end up being one. Like in Nicolas one.
Yeah.
And like, is this just true for specs? Or is this true for like the larger class of spectra?
It's true for any scheme.
Any scheme.
It's true for any scheme. It's
Localic. So any
yeah.
infinity topos that comes from a one topos. So like sheaves, if it's a coherent topos that's sheaves on a site that's really a one category with finite limits, then it will be true.
Thank you. Yeah, exactly. So that's right. So the truncatedness of the Galois category is connected to for a general topos is connected to the localicity of the topos. So if I had a topos that was essentially generated from like sort of freely generated from an N topos, then the Galois category would be an N category.
Yeah.
N equals N. Yes, N equals
Yeah, n equals n in this case.
N equals N. So I didn't, there's no shift. Okay, so let me just tell you some fun facts about this Galois category. So let's look at spec of a field K. This is what you think it is. It's the classifying space of the absolute Galois group of your category or of your field. There's nothing else going on there. If I take this category, and I take its classifying space in the continuous sense. Well, actually, there's several different senses. Maybe you'll talk about this.
Yeah, I'll talk about condensed.
Yeah, so I'll let Peter tell you about the condensed version. So I'll tell you about the profinite version. So let's say that I take this category and I invert everything in it. I take the nerve of this category, if you like. So I invert everything in it. Now I've got a condensed space, and I'm going to profinitely complete that condensed space. When I profinitely complete that condensed space, what I get is what's called the Étale homotopy type, the finite, I'll emphasize. Étale homotopy type. So what does that mean? That means that when you think about this stratified space, this gal of X, you should think about this as giving you a stratification on this space, the Étale homotopy type. So this is a stratified homotopy type attached to your scheme. This is the profinite Étale homotopy type that you get from doing this. I think Peter's going to tell us about a fancier kind of homotopy type that they and Katrin and, well, okay. There's a list of authors, and you will remind me of it in your talk. Okay, so that's another thing. But now, okay, well, I also know another way. If I've got, say, a scheme over the complex numbers, let's say it's a finite type, I know another way to get a homotopy type out of this, right? Namely, I can take the complex points of that scheme. Right, so that thing is something that's glued out of subspaces of C to the N for various N's, maybe. So I can just use the topology on the complex numbers and induce a topology on this thing. This is the so-called analytic topology. So that's a topological space. I used the topology on the complex numbers to get it. But it's a topological space. So if you write down the equation for a torus, then what you'll see here is a torus, right? So it's good. Okay, so what does it have to do with this abstractly defined thing? Oh, let me emphasize something about this. Sorry, I have a point to make. This thing is stratified. It's stratified in kind of a dumb way, but it is stratified over the Zariski topological space. I said when I was going to write down this topology, I was going to put it up here, so I'm going to. There's this perfectly good map here. You send the point to the point of the Zariski space to which it corresponds. It's a perfectly fine map. This is a stratification. It might feel a little weird, but it's a stratification. It's a nice profinite stratification of this thing. So what does that entitle me to do? Well, that entitles me to take the exit path category of this thing over this thing. This is the exit path condensed category of this thing over this thing. And once again, I'll do a profinite completion. And it will exactly recover Galovax. So there's this, even though I used the complex numbers to produce this, this homotopy type actually agrees with something that is defined completely independently. This is a basically kind of fancy way of describing a theorem from SGA ultimately. SGA 4, I think.
And then from Galovex, you can recover the Atoll site.
I can recover the Atoll topos, yeah.
The Atoll topos, yeah.
Which theorem out of SGA would that be?
Well, so it would be the theorem that says that if you take the cohomology if you take the Atoll cohomology of X with finite coefficients, say, then that coincides with the cohomology of the complex points of the analytic topology with those same coefficients.
But this is much more than that, right?
It's actually, well, it's equivalent, in fact.
Ultimately, it's equivalent.
Well,
Well,
okay.
plus the
but
pi1 statement.
Some pi1 stuff, but
Yeah.
like, yeah, to say that for constructible sheaves in the Atoll topology, that, you know, the cohomology agrees, including this monabelian cohomology, is literally equivalent to the statement. But maybe it's not obvious that it's equivalent.
Wasn't obvious to us.
Just
a minute. Yeah. Yeah, I mean, this is sort of a structured version of that sentence, I would say. That's how I'd describe that. Highly structured version of that. Oh, okay, so. Okay, I need to finish up, so let me say one last quick thing.
You're taking so many questions doing, so you can go a bit into the question time.
That's all right. I mean, I don't mind. I think I'll just say, I'll say 2 minutes worth of stuff. So here's the 2 minutes worth of stuff. So what you see now is that if you take something like spec of a ring, then you can take its Zariski topological space, and that's a profinite poset. So it's a sort of a fancy poset. And then you can do something a little bit finer. You can look at the Atoll topology on that thing. And then you'll get this sort of finer invariant, this Galois category, which is a profinite stratified space. And that profinite stratified space completely recovers the Atoll topos. Right? So it's this very nice kind of fine picture of spec of your ring. So now suppose that I wanted to do this with not just a ring, but say a symmetric monoidal stable infinity tensor. So what we have is we have either the Balmer version or this other version that I talked about. We have this spec of spec. We have this Zariski topological space for a symmetric monoidal stable presentable category. So we have this Zariski topological space. And what I would love to see, but do not know how to produce, is an Atoll version of this same thing. If you have a symmetric monoidal stable infinity category, you expect to see an Atoll thing, an Atoll version of that thing. And what would be an example of this kind of thing? Well, a good example of this sort of thing would be that if you looked at, say, spec of the K-n local sphere, the category of K-n local spectra, then the Zariski topological space will just be a point, nothing going on there. But this thing, so let me actually write the words out so that you're not just staring at me yammering. If I look at the category of K-n local spectra, and I look at the Zariski topological space, well, not much happening there. But if I now look at the Étale version of the same thing, then what I should predict is that I'm going to get the classifying space of the fully extended Morava stabilizer group. I never know what the correct notations for these things are. The most extended one. And these things should fit together into a nice stratified space, stratified by spec of the sphere spectrum as the Zariski topological space. And you should be starting to think about what the gluing between the different levels looks like. As far as I know, all of this is not understood yet. I feel like it's a good idea to end on an open problem. So that's what I'm going to do. Thank you all so much. I appreciate it.
Very much. Any
Yeah.
If you pull down that board to the previous picture, this like geometric Langlands masterclass recently, and I don't remember much, but there was like this thing where when you have like something that is glued together from like point onion space along like a tubular neighborhood, you get like a loop group action by basically rotating the neighborhood, which like still fixes the point, and then you know it gives you an action on the whole thing. Do you get something similar here?
You were asking the best questions today. I can't answer any of them. It's a great question. I don't know what to say. I love that idea. I haven't. You have something to say about it?
No, but can I add a prediction?
Oh, please.
Second prediction, which I think is implicit, but so I mean, yeah, this is one normalization to check that whatever one creates is the right thing. The second one is that spec of QCO of X. Yes. Should recover the Galois category.
And I'll insist that it be the opposite. I like that.
Yeah, maybe that. Yeah. Depending on sign.
call.
What's that?
Like
Oh, yeah. This is the Étale version of it. Yeah,
Yeah.
thank you. Yeah, thank you. Yeah, thank you.
That's a name.
This is a prediction. These are predictions.
Yeah. I mean,
This is the dream board.
yeah.
This is my dream board. I have my vision board and my dream board.
But yeah, like certainly, whatever, if one wants to construct something called spec C et al., it has to satisfy these two.
That Robert and Dustin are thinking about. That would help a lot.
I think also in the 2D geometry community, there is kind of already a notion of finite étale in terms of separable algebras.
Yes.
Yes.
Thank you. Yes, that's right. So, for example, there's the paper by Akil Matthew. So and that's giving you these sorts of nice. So right. So that be incorporated into this story. That's exactly right. So stratum wise, that's telling you stratum wise, you sort of know what to do, and it should basically be the story that's, for example, in this paper by Akil Matthew. Thank you. I should have mentioned that sooner. But what's not at all clear is how to glue those pieces together to give you a Galois category. And what's still not clear to me, but might be clear to people like Robert and Dustin, is how to have an Étale version of this version of the spectrum as opposed to the Balmer style spectrum. I don't really have anything non-trivial to say about that. I'd love to know more. Do you have a thought?
One last question.
Yes.
Moving away from this like fancy setting, just in the classic algebra geometric setting, there are like 200 topologies. So Etal is Zariski is nice because it's simple. Etal is nice because you can build get a good grasp on it. But there are other interesting topologies.
Yeah,
Yes.
absolutely. So well, it's not very nicely behaved, but there is a small flat site. It has some functoriality issues that keep it from being as nice as you'd like, but it does exist and you can take its Galois category. And you get a condensed category. And let me be careful here. In the case of a field, you don't get anything new. But I don't actually understand what happens with the gluings in the Galois category. So like, you know, in the spider picture, like, I don't think anything changes when you pass to the flat topology here, but I think something can change here. And I don't fully understand how that works yet. So yeah, I mean, there are these finer topologies that are out there, and you can start to play with those things. We've done tiny little bits of that. So we've looked at things like the dual Etal topology and stuff like that. There's sort of interesting kind of branch covering things that you can catch with these Galois categories. So there's stuff like that you can do, but going deeper seems interesting.
Also because I think, right, no one actually knows what the points of the flat topos are.
Oh yeah, that's right. That's a big obstruction. No one knows what the points of the flat are.
That's the underlying category, is the category of points. So
Yeah.
if you don't know that to start with, it's hard to get going.
Yeah, totally. Yeah. That's an issue.
Makes sense for every profile in stratified space.
It makes sense. I would define a profinite stratified space in terms of its exit category.
Yeah, I was just wondering if you can take the exit path category of GALX. And if
Yeah, I mean, it is. I'm kind of eliding the difference between a stratified space and its exit path category. I'm just sort of pretending like they're the same thing, which I got permission to do from Lucas and Peter. So like, you know, when I'm talking about a stratified space, I'm talking it via its exit path category. I actually don't know more information than that in that sense. Am I answering the right question here? I feel like I'm not answering the right question. But like I say, I don't have a literal topological space with a literal stratification that I'm taking the exit path category of to get this thing. I just have the kind of raw data of the the stratified homotopy type. Is that clearer? So when I say stratified space, I'm often just talking about a stratified homotopy type. That's what I should have said.
Okay, then maybe one last question. Now that you are done with your mini course, what's the title? No, no.
Here. All right. So what was my title?
Wuthering Heights.
Still being recorded.
Thank you.
Let's thank Clark again for his mini course. Now we have